Multivariable Calculus, Section 12.4, Partial Derivatives. Now you'll recall that in single variable calculus we use derivatives in relationship to tangent lines. Well, partial derivatives give you tangent planes in 3 dimensions. Tangent lines and dy dx for single variable functions f of x. Let's review this. Here's a picture of a blue function. And if we use the blue dot and the red dot to form a line, that's a secant line, and its slope is delta y divided by delta x. If we let the blue dot slide down on top of the red dot, then we have a single point and a tangent line shown in red, and its slope is dy dx, the instantaneous change along the function. And so dy dx was the limit as delta x goes to 0 of delta y divided by delta x. And there's the familiar formula that we used in single variable calculus, the limit as h goes to 0, f of x plus h minus f of x divided by h. Now we'll look at tangent lines and derivatives for functions in 2 variables. And we have a slightly different symbol for a partial derivative of f with respect to x. And notice if we take our derivative of our 2 variable function with respect to x, we add the h to the x value, and if we evaluate that, we get the partial derivative with respect to x. And here are some different notations for the partial derivative of f with respect to x. We can use f or we can use z, and we can use various other symbols including the dx. The partial derivative of f with respect to y, we add h to y in our familiar formula and take that limit. And so here are the various and sundry symbols for the partial derivative of f with respect to y. Again, f can be z, we can use f, we can use z, or we can use big D for derivative. Now here's the geometric interpretation of these various derivatives. Let's say we have a surface in 3 space, and a given point on that surface, we'll call it ABC. If we look at the trace on this surface that is on a plane parallel to the YZ plane, that's called the Y curve through ABC, and it has a tangent line. Now, the slope of that tangent line is the change in z with respect to y, because it's as though we're ignoring x and just drawing a curve on the YZ plane, or parallel to the YZ plane, and therefore it's a change in z with respect to y. But we use the partial derivative symbol because we're really referring to a function in x, y, and z. Now if we draw a trace using a plane parallel to the xz plane, then we have what we call the x curve through ABC, and it's parallel to the xz plane, and it has a tangent line. And again, we're treating y as though it wasn't there, and we're just looking at the relationship between z and x. And so the slope of that line is the partial derivative of z with respect to x. So now we're going to look at the equation of the plane tangent to the surface. Here's our picture again with our x curve and its tangent line, and our y curve and its tangent line. And if we draw a vector on the line tangent to the x curve, the slope of that line, remember, is the partial derivative of z with respect to x. So the equation in the xz plane would be z equals mx, or z equals the partial derivative with respect to x times x. And so that vector's components then, we're going 1 unit along, if we go 1 unit along the x-axis, then we're going the partial derivative of z with respect to x along the z-axis, and we're not moving along the y-axis at all, so the j component is 0. Now if we look at the vector on the tangent line to the y curve, the slope of that line is the partial derivative of z with respect to y, so the equation of that line, if it were on the yz plane, would be z equals my, or z equals the partial derivative of z with respect to y times y. And so that vector's components are 0 along the x-axis, there's no I component, and if we go 1 unit along the y-axis, for the j component, then the z component, or the k component rather, would be the partial derivative of z with respect to y. So you'll recall from a previous section that if we cross two vectors, we get a vector perpendicular to both of the original vectors. And so for our normal to the plane, we're going to cross Vx with Vy. And to do that, we're going to evaluate it with a determinant. We take the determinant of those two vectors that determine the plane that's tangent to the surface, and we evaluate that determinant by using the diagonals and then taking the bottom vector minus the top vector. And so that's our normal that would be pointing straight up from the surface. Now those negatives are a bit unfortunate, so we'll use the normal pointing in the other direction, down from the surface. And so there it is in component form. Now here's a picture of the point ABC on the surface and the plane that's tangent to the surface. And let x, y, z be any point on the plane, the tangent plane. Then we can take a vector on the plane, a generic vector on the plane that can represent any vector on the plane, and its components using head minus tail would be x minus a, y minus b, and z minus c. Now you'll recall from a previous section that if we dot the normal with any vector in the plane, we get 0 because every vector in the plane is perpendicular to the normal by definition. So we're going to go ahead and dot those two vectors, and we get this form of the plane. And of course zx and zy will be numbers at that particular point. Now the book writes it this way, and sometimes in the answer book they multiply it completely out. Compare that to the equation of a tangent line in single variable calculus, and you can see there's some similarities there. We have the function value minus something equal to a slope times a single quantity for single variable calculus, but we have two different slopes times two different quantities in our three-dimensional example. Computations of partial derivatives. Now we're not going to be using the limit definition. We're going to be using all the shortcuts we already know. To compute the partial derivative of f with respect to x, we treat x as the independent variable, and we treat y as though it were constant because we're only looking at the change in the zx, the xz plane. So for example, if I want to take the partial derivative with respect to x of this quantity, anything that doesn't have an x in it is just a constant. So the square root of 2y will go to 0. The first term will just have a regular 2x as its derivative. And the middle term, we treat 3y to the fourth like a constant. So we just bring the 5 down and change the x to x to the fourth. And then the third term, we treat y as a constant. So it's like mx. The derivative of mx is just m. So in this case, the derivative would be y. So we have 2x plus 15y to the fourth, x to the fourth, plus y for our partial derivative. Now to compute the partial derivative of f with respect to y, we treat y as the independent variable and x as though it were constant. So here's another example. And in this case, any term without a y is just a constant. So the x squared term, for example, would go to 0. And then in the second term, 3x to the fifth is treated as though it were a constant, and we just take the derivative of sine y. And then in the third term, xy, x is treated as a constant, and so the derivative of a constant times y is just that constant. And then the last term, there's no x in it to bother us at all, so we just bring the 6 down and reduce the power. So we get 3x to the fifth times cosine y plus x, and then in the last term, 24y to the fifth. So these computations are actually fairly simple. Partial derivatives for functions in 3 variables. Well, this time we have 3 partial derivatives, one with respect to x, one with respect to y, one with respect to z. So if we want to use a letter instead of f, we usually use a w. For example, let's look at the partial derivative with respect to z of this function in 3 variables. Well, any term that doesn't have a z goes to 0. So that second term is going to go to 0. The first term we treat x squared as a constant, so it's just going to be a constant times z, the derivative of which is that constant. In the third term, the 3 will come down in front and reduce to z squared, and the xy just stays there like a constant. And in the last term, 5y remains as a constant, and we take the derivative of cosine z, which is negative sine z. So our answer is x squared for that first term. And then we have in the third term, we keep the xy, the 3 comes down, we have z squared. And then the last term, the negative sine z changes the negative sign to a plus, and we keep the 5y because we treat it as a constant. Now, so far we've looked at first order partial derivatives. We've only taken the derivative once. Those are first derivatives. In this context, they're called first order. So now let's look at some second order partial derivatives for functions in several variables. One symbol is fxx, and it's a little strange because the parentheses are assumed around the first part. And if you're taking the derivative with respect to x and then with respect to x again for your second derivative, there's never any confusion with the notation. However, if you have two different variables that you're going to consider, the parentheses in that first notation are considered to be around the f sub x. And so when you rewrite it in the Leibniz notation, the x and the y are switched. So in this notation, which I actually prefer, it means take the derivative with respect to x first, and then take the derivative of that result with respect to y. And so if we have f sub yx, that means take the derivative with respect to y first, and then take the derivative of that result with respect to x. The first variable, use that first, and then take the result and take the derivative the second time with respect to that second letter. Now here's a list from your text of the various, the 4 different combinations, fxx, fxy, fyx, and fyy. And notice that if you have two variables in the f notation, the x comes first. Well, then in the Leibniz notation, the y comes first in the denominator. And so I don't really use that last column of notation much. I prefer the f notation, Newton's notation. Here's an example of second order derivatives for this particular function. fxx, first you take the derivative with respect to x, so the x squared goes to 2x. The y cubed there at the end will go to 0, and then the middle term you just treat 2y squared as a constant times x, and the derivative of a constant times x is that constant. Then you take the derivative of what's in the parentheses with respect to x, so the second term goes to 0, and the derivative of 2x is just 2. f sub xy. First you take the derivative with respect to x, and that's the same as the first step in the first part of the example. And the second time, though, now you take the derivative with respect to y. So the 2x goes to 0, and the derivative of 2y squared is 4y. fyy, first you take the derivative with respect to y, so the x squared term goes to 0. The second term, the 2 comes down and multiplies the pseudo-constant 2x by 2 and gives you 4x, and then y to the first, and then the derivative of y cubed is just 3y squared. Now the second step, you take the derivative with respect to y. So in the first term, 4x is treated as a constant, and that's your derivative, and in the second term, the 2 comes down and you get 6y. And finally, fyx, you take the derivative with respect to y first, so that's the same as the first step in the previous problem, but then you take the derivative with respect to x, so the 3y squared goes to 0, and in the first term, 4y is treated as the constant times x. Now you may have noticed that fxy is equal to fyx, and this will always happen if you have continuous first and second order derivatives. So if f has continuous first and second order partial derivatives, then f sub xy will equal f sub yx. Here's an example of a third order partial derivative, fyxx. Well, first we take the derivative with respect to y and treat x as a constant, and we did that in that last example above. Then we move in and take the derivative with respect to x, which we also did, but the 3y squared goes to 0 again, and we just get 4y as the constant multiplier of x. And then the third time we take the derivative with respect to x again, and therefore the 4y goes to 0. All right, now some examples from your text. Number 4, compute f sub x and f sub y given f of xy equals e squared times e to the xy. Well, for x, the e squared is a constant, and we take the derivative of e to the xy using a chain rule. So it's just e to the xy times the derivative of xy. And if we're taking the derivative with respect to x, then the derivative of xy is just y because it's treated as a constant. And then I just rearranged it a little bit. F sub y of the quantity is the same idea, except when we take the derivative of xy during the chain rule. Now y is your variable and x is considered a constant, and so the derivative of xy is x instead of y. Number 10, compute f sub x and f sub y given this function. All right, this is a nice review of all your derivatives. You have to remember that the derivative of tan inverse of a quantity is 1 over 1 plus that quantity squared, and then if that quantity is a function, you have to apply the chain rule. So f sub x is 1 over 1 plus the quantity xy squared times the derivative of xy, which with respect to x is just y. And then if we do it again with respect to y, it's the same idea, except that in the chain rule again, the derivative of xy with respect to y is just x. Number 14, compute f sub x, f sub y, and f sub z given this function in 3 variables. Well, for f sub x, the second term goes to 0 because there's no x in it, and so we just get the derivative of x to the 4th. For f sub y, we ignore the first term, it goes to 0, and then we treat the negative 16z as a constant times y. And finally, f sub z, again the x to the 4th goes to 0, and we treat the 16y as a constant times z, and so the derivative is negative 16y. Number 22, verify that f sub xy is equal to f sub yx for this function. Well, for f sub xy, first we take the derivative with respect to x. So the first term becomes 6x squared. The second term, the 2 comes down, and the 5y is treated as a constant, so we get 2 times 5y, which is 10y. And then the minus 6y squared goes to 0 because we're taking the derivative with respect to x. And then in the last term, y to the 4th is treated as a constant times x, and so we get y to the 4th. Now we're going to apply the partial derivative with respect to y to get our second derivative. And so the 6x squared goes to 0, and the 10xy, 10x is considered the coefficient of y, so we get that. And then the derivative of y to the 4th is 4y cubed. Now we're going to look at f sub yx. So first we take the derivative with respect to y. And so the 2x cubed goes to 0. The second term, we treat 5x squared as a constant times y. The next term, the 2 comes down and we get 12y to the 1st. And then in the last term, we treat x as a constant. The 4 comes down in front of it, and we get 4xy cubed. Now we're going to take the derivative of that quantity with respect to x. So the middle term is going to go to 0. The first term becomes 10x, and the last term we treat 4y cubed as the coefficient of x, and so the derivative of a constant times x is just that constant. And sure enough, they are the same. Number 34, write an equation for the plane tangent to this function at this particular point. So remember that the normal is the partial derivative with respect to x for the I component, the partial derivative with respect to y for the j component, and -1 for the k component. And so we have to compute those partial derivatives. So we keep the constant 4 over pi, we apply the derivative of arctangent, and then we multiply by the derivative of xy with respect to x, which would be y, and then we plug in 1 for x and 1 for y, and we get 2 over pi for the partial derivative with respect to x at that particular point. Then we compute the partial derivative with respect to y, which is almost the same, except now the derivative of xy is x. So when we apply the chain rule, we multiply by x instead of y. But again, when we put in, since x and y are both the same number, both are 1, when we plug in 1 for x and 1 for y, the partial derivative with respect to y is also 2 over pi. So then we dot n with our generic vector on the plane. The vector on the plane is x minus 1, y minus 1, and z minus 1. And when we dot those, we get this, which is a perfectly fine answer, but the fractions are a little tacky, so I multiplied through by pi. Now, in the back of the book, sometimes they rearrange it, sometimes they don't. So you may have to multiply that out to get your answer to match the book. Number 40, write an equation for the plane tangent to this function at this point. So the procedure is exactly the same. The partial derivative with respect to x, you bring the 1/2 down, copy the inside, it's all to the -1/2, and then the derivative of the inside with respect to x is 2x because the y squared is considered a constant and goes to 0. And then we plug in our numbers for x and y, namely 3 and -4, and simplify to 3/5. Same procedure for the partial derivative with respect to y, except this time when we apply the chain rule, the derivative of the inside function is 0 plus 2y. Plug in the numbers again, and we get -4/5 for that partial derivative. And so then we take our n, our normal vector, which is 3/5, -4/5, and then -1 for the k component, times our generic vector on the plane, which is x minus 3, y minus -4, and z minus 5, using the ABC point. And when we multiply that out, again, this is a perfectly good equation of the plane, but the fractions are a little tacky. So multiply through by 5, and then if you like, you can multiply all that out too. Number 42. Can f of xy exist given these partial derivatives? In other words, did someone do a correct calculation, or is this just a lie? So the book's method is to compute the fxy and the fyx from these partial derivatives to see if they're the same, because obviously these are all polynomials, so all the derivatives should be continuous. And if so, then fxy should equal fyx. So we take fx and we take its derivative with respect to y, which gives us 5x plus 2y. And then we take our fy and take the derivative with respect to x, which gives us 6x plus 2y. Now, the observant person will notice these are not the same, and therefore this is a lie. No such function exists. But I say, why not integrate? For example, we could take our f sub x derivative. Someone has taken the derivative with respect to x, so we just go backwards. And so y is treated as a constant, and so in the first term we integrate 5x and get 5 x squared, keep the y as a constant. And then the antiderivative of y squared, if it's just a constant, would be y squared times x plus c. Then we take our fy and integrate with respect to y. So we treat 3x squared as a constant, and then the antiderivative would just be 3x squared y. And then we treat 2x as a constant, and the antiderivative of that would just be xy squared plus c. And the casual observer will notice these are not the same. Therefore, no such function exists with these particular partial derivatives. Number 44. Can this function exist given that these are the partial derivatives? Well, the book's way is to take fx and take the derivative with respect to y, And when we do that, cosine x just hangs around like a constant, and the derivative of sine y is cosine y. And f sub y, we take the derivative of that with respect to x, and so cosine y hangs around like a constant, and the derivative of sine x is cosine x, and voila, they are the same. Therefore, such a function does exist. Yes, fxy equals fyx, hence the function does exist. Well, let's just integrate again and find the darn function then. So I take fx and integrate with respect to x, which means sine y stays the same, but the antiderivative of cosine is positive sine x. Take fy and integrate with respect to y, because they took the derivative with respect to y, so we have to go backwards using y. So sine x just hangs around as a constant, and the antiderivative of cosine y is sine y. And then don't forget plus c. So yes, these are the same. Both partial derivatives integrate to the same function, and therefore that is the function f of xy in this problem. But the book didn't ask you to find that, so I just went a little further. So now I'm going to leave you with a female's dream come true, perpetual chocolate. You take the candy bar, you take a little piece out of it, rearrange what's left, and voila, you have the same candy bar back again. And you just keep repeating that process and fill your cup with an infinite amount of chocolate. You can ponder that while you work the problems in section 12.4.